All right, trust you did well on your test. Students in here did a very, very good job, so very, very pleased with how students did on their test over measures, chapter 6. We're going back now to chapter 4. Now that we understand measures, lengths, and things like that, let's go ahead and talk a little bit about geometry that builds off of that idea of measurement. You're on page 142 in your textbooks. Page 142 in your textbooks. Have a pencil or highlighter just to mark some different things here in your book. And if you would, mark that first sentence. Geometry is the study of the properties, measurements, and constructions of flat figures and solid figures. The study of the properties, measurements, constructions of flat figures and solid figures. By flat figures, we're talking about things that you could draw on your paper, things I could draw on the chalkboard. I can draw a square, a triangle, a circle, things like that. I can't necessarily draw a basketball. Now, I could draw the illusion of a basketball. I could, if I were really good, and I'm not, but if I were, I could draw something that looked 3D. But really, truly, you couldn't pick it up off the board and dribble it, right? You couldn't really even throw it at anybody with any effectiveness. An actual solid object doesn't fit on a chalkboard, right? Those are solid objects versus flat figures. You notice the word geometry, this is your fourth line down, actually means to measure the earth, or earth measurement, if you're being a little more literal about it. But if you mark that, geometry actually means to measure the earth. Geo meaning earth, metry referring to measurement, so to measure the earth. Because the use of geometry is that which could measure anything on earth. Note this guy's name. It says around 300 BC, a Greek mathematician named Euclid, mark his name, Euclid, wrote a book entitled The Elements. Mark the title of his book as well, if you would, please. That is still used as the basis for geometry texts today. When you are in, I think it's going to be 11th grade probably, you're going to take a class in plane geometry, and The Elements that Euclid wrote was actually a collection of books. How many have seen an encyclopedia set in the library? It's one encyclopedia, but it takes like 26 books to fit everything in, or however many books it is. I don't actually remember. It's 22, excuse me, because they combine some of the letters that have not as many topics. Well, The Elements was 13 books. It was a 13-volume set. When you get to high school plane geometry, the class you're going to study is going to use the first 5 books of The Elements and combines them into one study of plane geometry. So make sure you know that guy's name, class. It is Euclid. And what was his book entitled? The Elements of Geometry. And so he was the father, if you will, of geometry. He didn't invent it, okay? Everything, he just discovered things that God had already put into place. But he kind of put things in a methodical way. As we study geometry, we need to understand several different concepts. And we're going to start this chapter just talking about plane geometry. Next chapter, we'll get into the solid geometry stuff. But for this chapter, we just want to focus on plane geometry. So it begs to know, what is a plane? You see that term already in bold there. Mark this, if you would. A plane is a flat surface that extends infinitely in all directions. A flat surface that extends infinitely in all directions. Now, does such a thing actually exist? No, because you can't have an infinite plane, but the idea is that which is infinite. This chalkboard is a flat surface. Imagine, though, like if I'm writing on the chalkboard, when I get right here, I run out of room, correct? I can't keep writing. Imagine if the chalkboard somehow in this magical world could just keep getting bigger and bigger, as big as I wanted it to be. So I'd never, ever run out of room. And I could go down as far as I wanted up. That would be a plane. But in general, a plane could be any flat surface. So, for instance, in this room, there are a whole lot of planes. What would be a plane? Sam? Okay, the flat page of the math book. Now, that page there is kind of curled, right? So that would, but the flat page of the math book would be a plane. The surface of the desk, or for me, the lectern. The floor could be a plane. Now, technically, there's a little bit of a bumpiness to the floor. Any of you ever tried to put a piece of paper on carpet and write on it, and you discover that doesn't work too good? So my kids, when they want to draw, instead of sitting at the table, which would make a lot of sense, they sit on the kitchen floor while I'm trying to cook breakfast on Saturday morning or something, and they're right down there, and I step on them, and they try, and it's just kidding. I usually just tell them move, go sit at the table. But anyway, they like to draw on the not on the floor itself, but put the paper on the floor. This wouldn't work as well, but relatively speaking, unless you get down really close, it's a flat surface. Elaine?
The top of the bookcase.
Okay, the top of the bookcase would be a plane. One more, Ben.
It's not in this classroom, but a
plain, like the desert plain.
Okay, so and the reason we call it a plain, if you go out on the Great Plains of America, is just flat as far as the eye can see, except for wheat fields or cornfields, which, yeah, so anything flat is a plain. Plain figures then, and you see this notation, maybe it's not in here after all. Write this off to the side. Plain figures are figures that can be placed within a plane. Plain figures are figures which can be placed within a plane. If you can draw it on a piece of paper, it's a plain figure. That makes sense? So that's what we're going to talk about today, are plain figures. Things you could draw on a piece of paper. Okay? A basketball, no. A box, no. But some different things that you see here. Look at table A and put a big star next to this box. I'm not going to have you highlight stuff within the box because, like, it's already in the box. It's already nicely organized for you. So I don't think we need to waste highlighter or pen. Just put a star next to the box at page 142. Goes up to the top of page 143, table A. The first thing you see there is, it looks like a dot. And class, it's called a point. And we represent points, by the way, notice with capital letters. They chose to call this point, point A. We'll make a dot. And I could call this dot S for Sam. That's the Sam dot, okay? It's a point. Technically, a point is infinitely small. Problem is, if it were infinitely small, could we see it? No, we couldn't see it if it was infinitely small. That's why we use microscopes to see things like single-celled organisms. But we'll use a dot, but we understand a point is technically of infinite smallness. All right? If we were to have a whole bunch of points all in a row, well, it's really impractical to draw it like that, right? So instead we would just draw this. And really, truly, to go to infinity, to the end of this infinite plane, and to the end of that infinite plane is impractical. So we just put little arrowheads on the ends, and we call this, class, a line. A line is simply a length made up of points extending indefinitely. Again, since it's made up of points, it is of infinite thinness. Infinite thinness. It has infinite length, but is also infinitely thin because points are infinitely small. You can either name a line based on 2 points in the line. For instance, I could call this line JR if I wanted to. I might not want to, but maybe I do. I could call the line JR based on 2 points, or I could just call it by a lowercase letter. I could just call it B, for instance, if I wanted to. Okay? And so either 1 lowercase letter or 2 capital letters used to notate a line. Notice the way we notate this. If we wanted to, we could just say JR like this. This means line JR. If you use a single lowercase letter, you actually have to write out the word line B. Okay, so depending on how you want to name the line, you can notate it that way. However, thinking practically, can I do anything with a line that goes of infinite length? Not really, right? Like, even in Star Wars, an infinitely long lightsaber could cause real problems, right? You'd be destroying a whole bunch of stuff you don't need to destroy. It needs to have a finite length, right? Which is why it can't just be like a laser sword, because a laser could extend indefinitely, but it has a length predefined on it. What we want then is a line but just a piece of the line. Because if you have a piece of a line, I could take another piece of a line, another piece of a line, I could start making shapes, right? So most of what we deal with in plane geometry then, class, isn't actually lines, they're line segments. And you see that as the next thing. A line segment is a portion of a line having 2 endpoints. So instead of having something really, really long, maybe I have something shorter. Now at this point you have to have 2 points. This is now just a segment of a line. Line segment JR. How would I notate that? Well, instead of having JR with a line with arrowheads, I just have a line like that. We don't necessarily have to draw the dots at the end of it here, but this would be a line segment. Do we understand the difference between a line and a line segment? Line goes off infinitely, like the number line, to negative infinity and positive infinity. Really, no practical value to that. So we use line segments instead, which do have practical value, bounded by 2 endpoints. The next term you see there, class, is the term ray. A ray, think of a ray of sunshine. It has a definite beginning, right? Where do all rays of sunshine begin, class? The sun. And then they go infinitely out through space until they eventually reach Earth and go on to other places as well, right? How many of you have noticed that you can see certain planets in the sky? This morning, I don't know if you happen to notice the moon. It's about a half moon this morning, and near it looked like a really bright star. That was Venus. You were still seeing it. If you look in the night sky in the early evening, maybe you're out driving and it's 8, 9 o'clock at night, you'll see Jupiter was out, visible. So how do we see them? Well, sunlight rays reflect off of those planets and we see them. And so that's rays. A ray has a definite beginning point, an end point, and then it goes infinitely in one direction. Well, we have to pick a random point along there somewhere to name it, so we might call this LZ. Not lazy, just LZ. And we would notate this, LZ, and the arrow would go through. If Z is the secondary point as opposed to the origin point, we have the arrow over the Z. So a ray goes infinitely in one direction. Again, infinite really help us out a whole lot? Not really, other than the thought that things could extend. Now, if we were to, next page now, take a couple of rays and start at the same point. So we have a second ray now that also starts at L. And this could be, I don't know, X. No, okay, whatever, X. Okay, so we could also have a ray LX. Okay. Well, if these two rays start at the same point, they form with each other, class, an angle. An angle is simply two rays. Now, you could do the same thing, by the way, with two line segments, couldn't you? You don't necessarily have to have two rays. You could have two line segments. Maybe call this point E, for instance. You could have two line segments that also form an angle with each other. It doesn't have to be two rays. In this case, we've got two rays. But it forms an angle. And the angle, there's a few different ways you can name the angle. I want you to look at the notations here. I can name the angle. Notice the little symbols. Just draw a little angle. X, L, Z is one way to name this. Or, watching up here, I could name it Z, L, X. Start at one end of the ray, if you will. Go to what we call the vertex. Is that term in your book?
Yeah.
Yes, make sure you know that term. The vertex is the common point that the two rays share. The vertex has to be the middle letter. Does that make sense? So you can start at one end, go to the vertex, out to the other one, or from that one to the vertex, out to the other one. Or you could just call this angle L. So coming over here, what's one of the ways we could name this angle? Jalen?
EJR.
You could name it angle EJR. What's another way we could name it, Michael?
Angle J.
I like your laziness. I love it. Angle J. You took the easy one. Kirsten?
Angle RJE.
Angle RJE. These are the three different ways I could name that angle there. Or, if you really wanted to reduce it down, you could just call it a number and call it angle 1. If there's a number there, okay, and we will get to problems where we're going to want to number some angles just to make our life a little bit easier. For instance, by the way, if you will note this, we call these lines that these rays are referred to as the sides of the angle. I don't know if they have that term in your notes. They do not. So if you'll write that down, that the sides of the angle are the rays or the line segments. Note that term, the sides of the angle. Corey's sitting up nice and straight. And I just realized my picture is frozen.
Again?
Oh, no, it just unfroze. That was really weird. It was frozen. It is unfroze. I don't know. This thing's having issues. We need to get it fixed. And this is twice now in the same week. All right. The sides of the angle are what we call the rays or the line segments. So this is the vertex. These are the sides. Now, you could have a couple of lines or even line segments that instead of meeting beautifully at one point, you have this line and you have another line. And they happen to cross at a particular point. These lines are simply intersecting lines because they're lines that intersect or cross. How many have heard of an intersection out the street, right? It's where two roads meet up, right? And parents always say, be careful crossing the intersection because you got to look 4 ways instead of just 2, right? Cross one street, look 2 ways. Cross at an intersection, there's a lot of ways you got to look. Make sure people aren't turning right into you and stuff. All right, so intersecting lines. Notice how many angles are formed by these intersecting lines, class?
4.
4 different angles. Angle 1, 2, 3, 4. And it's times like this that it's helpful to number angles as opposed to trying to refer to them with names. If we call this point, for instance, I don't know, Q, and I call this point here A, B, C, and E, for instance, that I could call this angle EQC, an angle AQE, an angle BQA, an angle BQC. I could name them that way, but we're lazy. You say, well, Michael over there was like angle J, and you're like, well, this could be angle L. Why don't I just call this angle, for instance, angle Q? What do you think? Michael?
Because most of them, all the angles have the same beginning.
Which angle Q are we talking about now? Do you see that there's 4 different angles at Q, right? So which angle Q? So that's why we can't just use one letter, and that's when it's really helpful to number angles. We'll look more at that in the days ahead. Yes, Jalen?
Couldn't you like put angle Q4 or like angle Q1 or something?
Well, but if I'm numbering, I just call it angle 4. That's even easier, right? Lazy. I like it. Right? Be like, yes, sir.
Is the limit for the letters 3?
For a particular angle? Yes, yeah, you wouldn't, I mean, we wouldn't want to be like, and let's call this one D, and let's call this one J, and this one F, and we can call this angle ADJFQE. We don't do that. Does that make sense?
Yeah.
Yeah, because we're lazy, we don't want to do that. Yes, sir?
For the notation, is that how we write it? Do we have to write the and?
Well, if the question were to ask, for instance, let's go back to here, and I hadn't quite gotten there yet, so you're a bit ahead of me there, Michael. But if we were to say, how would we notate these lines? Well, the names of the lines, class, are AC, we don't have to include the Q, and BE. So we could have line AC and line BE, right? There's not anything special about the lines when they intersect. They just happen to be intersecting lines. So you just indicate I've got this line and I've got that line. You could say they intersect at Q, but we can kind of tell they intersect at Q because, there's a dot there. All right, the next type of lines are special intersecting lines. And these are lines that intersect at what's called a right angle. Now, most of you know a right angle has how many degrees, class? 90 degrees. Why do you suppose we call it a right angle? Sam? Ooh.
It's like shape of an L. Like it's
Shape of an L. L. Right angle. L. Ben?
Because it's exactly 90 degrees and it has a little square and it whatever.
Yeah, but why would we call it right? That seems like an odd name to use.
Because it's like perfect, like perfect,
What do you mean perfect?
like there's no
Slantiness, right? There's no
like, perfect
slantiness.
straight line.
So why don't we just call it a not slanty angle? Why right angle? Like, it almost sounds like there's such a thing as a wrong angle.
Right angle is like just an easier name because right and perfect are like the same thing.
Michael?
Because we're lazy?
No, not maybe. Here's really the reason. Think about in building, in this room. Do you see all the right angles in this room?
Yep.
It would be wrong, wouldn't it, if the floor were like this and the wall were doing that number. That would be wrong construction. This is right construction, right? Now, there are such things as vaulted ceilings, okay? So that doesn't necessarily have to only use right angle. This room is very much a box, right? Every corner is a right angle, floor to ceiling right angle, or a wall to ceiling right angle, wall to floor right angles, okay? But it's because generally speaking, in construction, the right way to build is to have a perfect 90-degree angle. So literally, right as opposed to wrong, yes. But right angles, right? If these lines were to cross to make right angles, which right now they don't, right? So they're kind of slanty with each other, but maybe more like that. At this point now, we'll go with our A and point C. Now we would describe the lines not just as intersecting, there's a special term for it, class, and we see that big long word, perpendicular. Class, say that word with me. Perpendicular. Perpendicular lines form right angles, and you're going to tell because they're going to put a little box in the corner. Now, in this case, in their picture, they actually have the box drawn in all 4 corners. I'm usually lazy. I'm going to only draw it in one of them because, after all, if you've got it in one of them, it has to be there for the other 3. Okay? But they drew it in all 4 corners. That shows that they're right angles. Well, now instead of just saying, okay, you've got these 2 lines, AC and BE, we can state not only do I have them, but they are perpendicular to each other. Your symbol is an upside down T. That upside down T is your symbol for perpendicular. And so you see in your book those perpendicular lines AB and XY are perpendicular. Questions on that? So if they just happen to cross, class, we just say the lines are, if they just happen to cross, they're intersecting. If they form right angles, now they are perpendicular. It is also possible that you get lines that are not intersecting. They are not perpendicular. Instead, they literally never intersect. Now remember, a line goes to infinity, right? Line segments don't, but lines do. So if I draw a line like this, and I have another line like this, that even if you kept going to infinity, they would never, ever, ever cross. Those lines that would never intersect are referred to, class, as being parallel lines, right? Parallel lines, lines that never intersect. So if I called this line, I don't know, JK, and I called this one BE, for instance, then we could say that JK, that line, is parallel. Notice it looks like an 11, just a little taller above and below, kind of where the line would be, BE. And this is how we'll notate parallel lines. So perpendicular lines, class, we use this upside down T looking thing. Parallel lines, we use that 11 looking thing. This shows the lines are parallel. How many say, I've learned all these terms before in a past year? These should have been reviewed for most of you. A couple of you that are saying, nope, I have not learned these. What that means then, if you haven't learned these before, you're going to have to put a little more time into studying, aren't you? All right, look down, if you would, with me now at page 143. Numbers 1 through 6, they've used some symbols, some notation. At your seats, I want you to write out in words what it's showing. What are they describing with those symbols? Do 1 through 6 on page 143. You're writing out in words what the symbol is describing. So they give you a symbol. Do you know what that symbol means? That's all they're asking. So number 1, class, what does that symbol mean? Angle. So specifically, which angle are we talking about here, Griffin, in number 1?
Just angle.
Which one? They named the angle for you. Angle, which angle? Angle A, B, C. We know the vertex of the angle, class, is what point? B. We know the sides of the angle will be AB and CB. Does that make sense? So number 1, what you should have in the blank is angle ABC. Seem easy enough? Look at number 2. What does that symbol mean, Corey?
Ray.
Ray. Specifically, which ray?
AB.
Ray AB. By the way, class, which is the end point or the origin point for the ray? A. Point A is where the ray begins, and it passes through some other point B. Number 3, what does that symbol mean, Elaine?
Line XY.
Line XY. So in the blank, you should have line XY, meaning X and Y are 2 random points on that line, or 2 points that the line passes through. Whereas number 4, Sam, that notation means line segment, KL. Meaning K and L are the end points of that line segment. Does that make sense? Number 5. Ooh, what are they telling us? There's a lot to unpack here in number 5. Ben?
Parallel lines.
Which 2 lines are parallel?
T and both of them.
What are the 2 lines?
T, Z, and XY.
Good. So we could say then that line TZ is parallel to line XY. Does that make sense? Line TL is parallel, or XZ, excuse me, not XY, to line XZ. Now again, class, which is easier, to write this or to say, excuse me, it was TL. That. Which one's easier to write, class?
That.
This one. This is why we use notation, because we are lazy. We don't want to have to write all that out. We'd rather just write that much, wouldn't we? So that's why we have the notation. We want to make sure we understand it. Number 6, what is that notation describing for us?
Angle V.
Angle V. Now, they only use one letter class, which tells me that V must be the vertex of the angle. I don't know what the sides are, but I know the vertex of the angle is V. Now you're going to flip it around. You're going to use the notation now. You get the easy job. They've given you a picture. You notate it. Number 7 through 12, 11 and 12 are on the next page. Do 7 through 12 now. You get to use the notation. Several students already finished. Question? You don't need to. Oh, okay, I see. Maybe I was misremembering the lines. Sorry. I thought it was like TL and XZ or something. It was TZ and XY? Whatever. Yeah, TZ and XY were the parallel lines in 5. Whatever. That's my short-term memory struggling. All right, number 7. What is that figure, Michael?
Line segment.
It's a line segment. Now, how do I label the line segment? What do I write on the paper?
Of like just a normal line on top, and then DE.
Is it DE?
TF.
DF. See, you do it too. All right, DF with a little line over the top of it. Good. How about number 8? There's a few different ways you could notate it. But class, what is the picture for number 8?
Angle.
It's an angle. Luciana, how did you name number 8?
Angle IJK.
Angle IJK. All right, what's another way we could name it, Bryson?
I named it same. I named it same.
On number 8?
Yeah, I named it IJK.
Oh, you named it the same way. What's another way we could have named it?
Angle KJI.
Angle KJI. Again, using this little angle symbol, or Jalen,
Angle J.
angle J would have worked as well. How many had one of those for number 8? How many had angle J, which was the easy way? Only Sam was lazy. Good. You had 2 different ways?
Yeah, I
All
put
right.
it in for
Number 9. What is that thing? What is that picture, Elaine?
Line.
It's a line, and how would we label this line or notate it?
Line ER.
And did you write out line ER?
Yes.
You wrote out the word line. There's a better way. What's the better way? Kirsten?
those, like putting something above it.
With the little arrows on it. There we go. Put a line above ER with little arrows on it. That's faster than writing out the word line. Now, if there were a single letter, like for instance, if they just called it E, we would have had to write out line. And by the way, class, if there's one letter, do we use capital or lowercase? Lowercase. When there's 2 letters, 2 points, points get named with capital letters. Lines individually would get labeled with lowercase letters. What about number 10? What is that shape or figure there, Ben?
It's a ray.
It's a ray. And how would we notate it?
PQ with a line over it
Like that?
and an arrow on one side.
Which side?
Right.
The Q side, right? Because P is the starting point. So we don't put an arrow on the P side, we put an arrow on the Q side there. Good. Turn the page. Number 11. How would we notate this one? Corey?
AB with a line over it with 2 arrows
Good.
on the sides. Then No. Perpendicular.
Good. What is the symbol for perpendicular, Corey?
Right angle.
Class? Upside down capital T. So this upside down T looking thing means perpendicular. Good. And then of course,
CD with a line up.
there we go. So line AB is perpendicular to line CD. And then what about number 12, Kirsten?
SD with the line over it and the 2 arrows, and then those 2 lines, like, yeah, and MN with the line over it and those 2 arrows.
There we go. How many had these for 11 and 12? Number 13 through 17, very quickly answer those questions. 13 through 17, very quickly answer those questions. Number 13, in geometry, what does a dot represent, Griffin?
Exact location of space.
Okay, the dot is used to represent some particular location, yes, but what do we call that exact location? We use a dot to picture it, but it's called a, Corey?
Point.
A point. A point is what a dot represents. It represents a point, which is some exact location in space, yes. Number 14, what's the name of the common point, or location in space, where 2 rays meet to form an angle? What's the name of the common point of 2 rays that form an angle for redemption, Griffin?
Vertex.
The vertex, very good. Number 15, what type of lines cross? Parallel lines or intersecting lines? Ben?
Parallel.
Parallel lines cross each other?
I meant intersect.
Intersecting lines cross each other. Yeah, parallel lines don't intersect. That's what makes them parallel. Number 16, what does a flat surface represent in geometry, Luciana?
Plane.
A plane. Good. And number 17, how many times do parallel lines intersect, class?
0.
0, never, none, however you want to say it. Look at the top of the next page. We talked about plane figures, right? Figures that can be drawn in a plane. Want to look at a couple of other terms there on that you see there. Do you see the term at the top of page 145? Closed figures. Closed figures. Mark the second sentence. Plane figures that begin and end at the same point are called closed figures. So, if I start at this point and I start drawing, and I end at the same point, that is a closed figure. I'm not quite sure what it looks like, but it is a closed figure. But I could also start at a point, and I could use straight lines. That is also a closed figure. I could start at a certain point, I could make a couple straight lines, and then loop back. That is also a closed figure. Closed, class, simply means it starts and ends at the same point. Now, a closed figure that is made up of only straight line segments is referred to as a polygon. And you see that as the next sentence, mark that also. Any closed figure that's made up of only straight lines, or line segments technically, is called a polygon. That doesn't mean that the parrot flew away. Okay, polygon just meaning many sides. Okay, poly meaning many, gon somehow meaning sides. Anyway, polygon. Closed figure made up of a lot of different sides. And you see table B has a whole lot of different polygons on it. Notice some terminology here, class. Each straight line that makes up a polygon is called a, are you reading with me? Side. Wait, that's what we called the lines that made up angles, sides. We're not very creative in the math world. We figured out side and we're going to stick with it. Also, notice, class, when 2 sides of a polygon meet, an angle is formed. And the point where they meet is a vertex. That's what we call the place where the 2 sides met of an angle. Yeah, it's also what we use for a polygon. So, the straight lines that make up polygons, class, are called Sides. And the place where they meet is called a vertex. Very good. Now, when we label some polygon, we will generally label every point with a capital letter. So we call this point A, B, C, D, E, F, G, H. And there's all the different points of the polygon, right? We have a little angle here at G. We have a little angle at D. We have an angle at C, an angle at B. Look at this angle at F, class. Looks like a Pac-Man. And we got another Pac-Man at A, which is kind of weird, and an angle at A. We got lots of little angles and sides and vertices, by the way. One vertex, two or more vertices. But we'll label our polygons with capital letters at every vertex. Now, if a couple sides happen to be equal, as I'm looking at this thing, I'm feeling like maybe BC and FG look to be about the same size. Do they look about the same size to you? If they're exactly the same size, we put a little tick mark or a hash mark on the side to show that these two things are equal. I don't know, kind of looks like maybe C, D, and GH are about the same. Like maybe GH is a little longer, hard to tell. But if lines are equal to each other, or line segments are of equal length, we'll mark them with those little tick marks. And you see some of those on those little polygons. Look at some of these polygons here, class. Three-sided polygon. Notice we call that, class, a triangle. We should all be good with triangle. We know triangle. Good. Four-sided polygon has a much fancier name, class. Quadrilateral. Now, this is where you got to stay with me here. Four sides. Quad meaning four, right? Quadrilateral, four sides. But if it's special, look at the blue one below the triangle. Notice, class, that the two sides that are going kind of slanty up are parallel. And notice the top and bottom lines that are horizontal are also parallel. We call that, class, a parallelogram. It's still a quadrilateral, but it's a special quadrilateral. For instance, you all are 7th graders, but only one of you is special enough to be named Sam I am. Right? Okay, so Sam is 7th grader. He's still 7th grader, but he's more special than that. He's Sam, right? Okay, so that blue thing, class, is a quadrilateral, but it's special. It's also called, class, a parallelogram. Now, we have another special parallelogram. It gets even more special, right? Because there is another Sam in our school. Nobody calls him Sam. They call him Samuel. Yeah, pastor's kid in 6th grade. He's also Samuel, right? So there's actually two Samuels, but we don't call him Sam I am. He gets that. Okay, so you could say like parallelogram, okay, and then we get more specific than parallelogram. If the parallelogram, class, look at that orangey red thing. Do you see that the sides are parallel and the top and bottom are still parallel? But it's not slanty anymore. They are right angles everywhere. That, class, we call a rectangle. A rectangle is a parallelogram. It's just more special than that. That makes sense? And a parallelogram is a quadrilateral. It's just more special than that. You want to get really, really special. Look at the yellow one down below the parallelogram, class. It is a rectangle, but all the sides are the same. So we have another name for its specialness, class. We call it a square. It's a rectangle, but all its sides are equal to each other. Oh, so is a square a quadrilateral, class?
Yes.
Because it has four sides. Is a square a parallelogram? Because its sides are parallel. Is it a rectangle? Because its sides are parallel and has right angles. It's just more special than all the other ones. Look at the green one. Class, we call that a rhombus. You don't have to roll the R. A rhombus. Now, a rhombus, look at the definition, class, is a parallelogram with all its sides equal. So look at the blue one. You see how you got long tops and bottoms and shorter slanty sides? But if you made all the sides equal, notice all the sides got one tick mark? Now it's got a special name. It's called a rhombus. Is a rhombus a parallelogram?
Yes.
Yep. Is it a quadrilateral?
Yes.
Is it a rectangle?
Yes.
No. Rectangles have right angles. Rhombus doesn't necessarily have right angles. Okay, but it is a parallelogram. It is a quadrilateral. Now, look at the tealy colored thing. That's not a parallelogram, but it's still a quadrilateral. See the tealy thing, four sides? Quadrilateral. It's special, but it's not got all of its sides parallel, class. It's just got two of the sides parallel, the other two ain't. That's called a trapezoid. Only two of the sides parallel. not both pairs parallel. You see the difference between parallelogram and trapezoid. All right? 5-sided polygon class we call a pentagon. Pentagon. Anyone know of a famous building called a pentagon? Where is it? Washington, D.C. Do you know who meets there? Military
Airplanes.
heads, right? Military heads, right? The Secretary of Defense, Secretary of the Navy, top brass, the generals, all them people. All right, 6-sided polygon class, we call that a hexagon. 8-sided polygon, we call that a octagon. Now, that's a funny looking octagon, isn't it? Where do we see a more normal looking octagon, Bryson? Okay, there we go. UFC, the octagon, right? We're in UFC, cage fight. Anyway, another more octagon that we would all see on an everyday basis driving to school, maybe. Ben?
Stop sign.
Stop signs, yes, are also octagons because they have 8 sides to them. How many of you, you're like, yep, I've learned all of these before, I'm familiar with these? How many say, nope, not seen these before? You've seen some of them before. All right, so most of us are pretty familiar with this. Turn the page. Actually, I think we'll save those terms there. Turn all the way, look over to page 147. Page 147, let's go through these real quick. Number 1, is a polygon made up of line segments, class?
Yes.
Yes, that is true for number 1. True. Number 2, quadrilaterals have 4 vertices.
No. Yes.
Ooh, we know they have 4 sides, right? 1, 2, 3, 4. How many points do they have?
4.
4 sides means 4 vertices. So yes, that is a true statement. We normally think of it as having 4 sides, but they do have 4 vertices. Number 3, vertices are labeled with capital letters, class.
True.
That is true. Make sure you remember that. Number 4, a triangle is a 3-sided polygon.
Yes.
That is also true. Number 5, a rhombus has 4 equal sides and 4 right angles.
False.
False. A rhombus does have 4 equal sides, but if it also has 4 right angles, class, we call that a
Square.
Rectangle.
square. A square. Now, a rectangle has 4 right angles, but it might not have 4 equal sides. The square has 4 equal sides and 4 right angles. Number 6, parallelogram has only 1 set of opposite sides parallel.
Trapezoid.
That's a trapezoid. The parallelogram has both sets of opposite sides parallel. The trapezoid, only 1 set of opposite sides parallel. For number 7 through 15, very quickly, write how many sides each of those things has. Number 7 through 15, quickly jot down how many sides does each of those things have? All right, let's take a look at these together for sake of time. Number 7, class, a rhombus has 4 sides, which makes it a quadrilateral. Square class, 4 sides. Quadrilateral, 4 sides. Octagon, 8 sides. Pentagon, trapezoid, hexagon, rectangle, 4, 2. By the way, what has only 2 sides? An angle. It's not a polygon though, is it?
Yes.
Because can 2 sides close up?
No.
It takes at least a 3rd side making a triangle to close it up, right? So 4 sides on the rectangle in the parallelogram class. Also 4 sides. Your homework for this evening. Homework for this evening. Page 144. Do numbers 1 through 8 in the homework section. Page 144, homework 1 through 8. And page 147, do the homework 1 to 17. Page 144, homework 1 to 8. Page 147, homework 1 through 17. One more thing to jot down. On your school supply list at the beginning of the year, you were told to have a compass and a protractor. You need those Thursday. That's lesson 63 for those watching. Okay, so compass and protractor, have those by Thursday. So you should already own them. It's just a matter of finding them in your lockers or finding them at home, bringing them to school. I'm going to be checking for them Thursday. So page 144, 1 through 8. Page 147, homework 1 to 17. Bring a compass and protractor by lesson 63. Have a wonderful Stacy and Sam rest of your day. You are dismissed.